Okay, thank you. As Bev said, my name is Tim Spielman. I'm one of the application engineers here at Alignex, specializing in simulation. So we'll get started with weld sizing and strength calculation. So I just kind of wanted to start off here talking about the different types of edge weld connectors that we have in SOLIDWORKS Simulation. Weld connectors in SOLIDWORKS Simulation. Just kind of wanted to start out with the different types of edge weld connectors available. So we have fillet welds and groove welds. Fillet welds, example shown here on the right, join two metal parts together at a right angle. As you can see here, we also have groove welds, which can join two or applied to a preformed opening or a groove between two metal parts, as shown here. So we have both single and double-sided. So you can see here examples of double-sided fillet and groove welds. Edge welds can be applied between two shell features or one shell and one solid feature. So this could be these could be two shells here, or this could be a shell and this could be a solid. The terminated part, we call this the terminated part here, always has to be a shell. So some of the terminology that we'll be using today, one of the main functionalities of edge weld connectors is that we can look at weld sizing. So when we talk about weld sizing and weld throat, this kind of illustrates what we're talking about here. So the weld size for a fillet weld is defined as the distance from the root to the toe, which is also sometimes called the weld leg. And then for a groove weld, it's the dimension of the joint penetration as shown here. And then the weld throat is always from the root to the face of the weld in both cases. So that's some of the terminology we'll be using. I'll jump into open up SOLIDWORKS here, and we'll get right into showing an example here. So this is kind of a simple example that will just illustrate some of the basic concepts, and then we'll actually get into looking at a more complex and realistic example. So kind of the overview and the objectives today is I'm going to introduce edge weld connectors, explain sort of when and how they can be used in SOLIDWORKS simulation, and like I said, I'm going to show this simple example, and then we'll move into a more complex example before we get into some of your questions. So first thing I'm going to do here is I'm going to start a new simulation study. I just go up to Study, New Study, and I can name it whatever I want, so I'll name it Webinar. And again, I've chosen static down here because it's just going to be a linear static simulation. And you'll see here that I've got a few parts listed up here in the parts area. So I've got the torque tube, which actually consists of a shell tube and this shell piece here, which is a little support, and then this back piece, which is a solid. I also have a bend piece here and another pipe. These are both shells, and then a back plate. So first thing I need to do is define a thickness here for all my shell features. So I'm going to go ahead and select all the shell features, right-click, edit definition, and I can select any thickness I want here. I'll just pick an arbitrary 0.1 inches. All right, and then of course when I created a new study, I have the default global bonded contact. I'm going to delete that out here because I'm actually going to create my own contacts and connections using the edge weld connector. So to get into edge weld connectors, I just right-click on the connections folder here. I'm just working right down the tree, so I'm in connections, right-click, and down here you'll see edge weld. And as I open that up, you'll see the first options I have here is a little drop-down menu. I get all the four types. So I've got fillet and groove, single and double-sided. And I'm going to start out here on this side, and I'm just going to work my way around the piping here. I'm going to pin this because I'm going to create multiple edge welds. So the first one I'm going to do up here on this edge right here will be a fillet, a single-sided fillet. So I select that from the drop-down. Next thing you'll see is I've got two face sets to select. So I always want to pick the terminated part in set 1. So the terminated part in this case, since this tube is terminating in this flat plate, the tube is the terminated part. So I'll pick this, and you'll see on the screen there, there's a little mouse, picture of a mouse with a blue arrow on the right mouse button. If I right-click, you can see on the left it dropped my selection down into the next window. So that allows me to make these selections on the fly. I can just create multiple edge weld connectors as I'm moving around, and it allows me to work very quickly. So again, I select face set 2, which is this back plate, and you'll see that right mouse button blue arrow again that drops it down to the intersecting edge, which is my final selection here. So I'll select this intersecting edge, and now you'll see that the area where the edge weld is defined is highlighted in this purple line. You'll also see a yellow sphere down here that shows the beginning and the end point of my edge weld in this case, and then a red arrow showing which side of the shell feature that the weld is located on. I can change that over here in my weld orientation. So what I'll do here is I can show you down here in the weld orientation. I'm on side 1 right now. If I select side 2, you can see that that red arrow flips to the inside. So I can flip back and forth the weld orientation. I'll keep this one on the outside. Moving down into the weld sizing area, I have 2 options here. I have the American standard and the European standard. So looking through the American standard, the first selection I have here is the electrode. So I can select from steel types up here and aluminum down here. And you'll see if I have one of the pre-selected electrodes chosen, it'll gray out this weld strength area. It'll automatically fill in that weld strength, and I can choose the units as well. So right now I'm showing for E60 a weld strength of 39,600 psi. If I want to create a custom electrode material, or if I have a different material, I select that right here. This is no longer grayed out, and I can specify the weld strength right there. So we'll just go ahead and select an aluminum electrode. And then moving down, you'll see under the safety factor, I have 2 default options here. And I'll kind of show you what those are referring to. So the safety factor, what it does is it reduces the allowable shear strength of our electrode material when it's doing the pass-fail check. So I have the ultimate shear strength of my electrode material divided by a safety factor, which gives me an allowable shear strength that this solver will compare against the actual shear forces that the weld is seeing at that location, and it'll help determine if I have a passing or a failing weld in that area. There's 2 default options down here, and you'll see it right here. I have the American National Standard for Automotive Lifts, which is a Automotive Lift Institute code, and if I hover over this, you'll actually see it says as per B153.1. It lists the actual code where that comes from. And then I also have the an ASME code. And both of those 2 default options have a default safety factor. So for the American National Standard for Automotive Lifts, I have a safety factor of 3 by default, and then the other option I have a safety factor of 5. I can also enter any other value that I want. So if I go down here, I can actually type in whatever safety factor value that I choose. And then my last selection is the estimated weld size. So I can choose to put this or not. If I uncheck this, it gets grayed out. But I can put in what my estimated weld size is for that weld, and that will serve to give me a comparison so that the solver can tell me if I'm passing or failing on my estimated weld size. And that'll make a little bit more sense when we get to the results. But basically, it's going to show me a comparison between what the solver calculates I need and what I'm specifying here. So we'll go ahead and create that first one. And I'll zoom in here and I'll create the next one. This one will be a double-sided fillet. So again, I need to pick the terminated part first. Right-click. And you'll see this one actually automatically detected that edge there and pre-selected it for me in that intersecting edges window. And I'll leave everything else in the weld sizing section the same. And now I have 2 more welds here that I'm going to create that are going to be groove welds because I have 2 parallel parts coming together. So I'll pick single-sided groove weld, think I selected the wrong ones there. There we go. And again, another single-sided groove weld. And then the last one, I'll zoom in and just create the final fillet weld on this face here. So again, I pick the terminated part, the next part, and the edge. Okay, so you can actually see here, highlighted in blue, all of my defined welds in there. And then if I go over and look in the simulation tree, there's a new folder under the connectors folder here called Edge Weld Group 1. So I can actually, if I wanted to create them separately, I could group these by type or however I wanted to, by location or material or whatever, however I wanted to group them. So I just have one edge weld group here showing all 5 of my edge welds. Okay, and then now we need to create some fixtures and loads so we can actually test this. So right now everything's unconstrained, so we'll put some fixtures in here. So I'll fix this back face here, and then I'll fix this bottom edge support right there. And then we'll just put in maybe some unrealistic, but just kind of some arbitrary loads just to show the effect of the edge welds here. So I'll put a gravity load so it's under its own weight, and then I'll put a force on the top of this side here. Okay, and now that we have everything defined, I can just go ahead and run this. Okay, and you'll see everything ran, and now I'm showing a von Mises stress plot here. So I'm going to turn off these other symbols so we can see a little bit better. So right now I'm showing a stress plot. If I right-click on my results folder, this is where we actually get into the weld check plot here. So if I right-click results, there's an option up here, define weld check plot. I have a few options in here, so I can include a title text, so I'll just call this weld sizing. And I can also associate a view orientation. So I'll pick the top view, click OK. And now you see I'm looking at a top view showing all the welds on here. And what it's showing up here in my check plot is that I have 3 welds that need attention and 2 welds that are okay. And so if I actually highlight one of these, so I've got edge weld connector 1 highlighted, it's showing me on here it needs attention because the calculated weld size is 0.33 inches, whereas the estimated weld size that I entered was 0.25 inches. I can cycle through and actually see all of the ones that are showing they need attention here. You can see this one, 0.26 versus my 0.25. The 2 that are okay are actually showing this one is about 0.04 inches, and this one is 0.247. Now if I click details over here, it will actually bring up some more details about the forces and moments on the weld at that location. So right now it's showing me where the edge weld is located, and it's showing me the weld size, the weld throat size, and some of the forces and moments on the weld at that location. So we can actually take a look at what it's showing us here. So the calculated weld forces, these are the 4 outputs that it gives us in that check plot. So the joint normal force is this one right here. It's actually normal to the intersecting shell edge. So it's this outward normal. Then I also have a shear weld axis force, which is this one here. That's actually parallel to the weld seam. Then I have a shear surface normal force, which is along the surface normal axis. That's this one right here. And then lastly, I have the bending moment about the local weld axis. So that's what it's showing me right here. And it'll show the min and max values of all those forces and moments, as well as the mean. Now I can output this to an Excel file. If I want to do that, and it'll output all those values. I can also click right here and get a plot of the calculated required weld size and weld throat size along the weld seam distance here. So starting from where that yellow sphere was located when we defined that, all the way around to the end of the weld seam. So this is showing the position along the weld seam distance on the x-axis here, and this is showing me the required weld size and weld throat size here. So you can see that it peaks right here at about 0.33 inches. So that's kind of a simple example. The other thing you can notice here is when I zoom in, these are all colored by pass-fail. So you can see this one and these two over here are showing red. Those are my failing welds that were calculated as requiring a larger weld size than I had actually input, and these two are showing in green because those are passing. So this was kind of a simple example. We'll take a look at a little bit more complex example. So this part is actually from a excavator. So this is where the cab would sit. And then there's actually a lifting arm located back here attached at these hinge points here. So what we'll take a look at, all of this is welded in here. So the first study we'll do is just a static study, looking at everything as a bonded contact. We'll kind of look at where the high stress regions are, and then we'll actually create some weld connectors in those locations to check our weld sizing and determine if we have a strong enough weld in that location. So this study has already been created for us. I actually set this up ahead of time, but I can kind of step through showing what it is. So all of these parts have already been converted to shell, and they've already had a thickness assigned. And you can see the material here is plain carbon steel. Under our connections, we have several contact sets here, so I just highlight them so you can see all the welded locations have been defined using local bonded contact sets here. And in this case, we're not using any weld connectors. We're just defining all the welds with bonded contacts. I've also defined on the back side here, at these hinge locations, I've defined some reference geometry fixtures to basically constrain these radially and axially, so they're only allowed to move as a hinge. And then lastly, we have a gravity force in the downward direction here, and then a remote load actually located, if you can see this here. This is actually modeling the force that would come from the cab sitting on this platform here. So you can see most of the forces in the downward negative y direction, and then there's also some side loading in the x and z directions. So I've already run this study, so I'll just show you, I'll throw up the results right here. So you can see the highest stress areas are in this bend region here. And actually this side has higher because of that side loading that's pushing it in the x and z directions here. So if I zoom in, you can actually see this is the highest stress region on the part. And this seam right here is actually welded. So this is the area that we're going to focus on and apply the edge weld connector to check our weld strength in that location. So what I could do is just right click on this study and duplicate it. So I'd have all the same settings, then I can go ahead and make my changes. So I've already done that here. I have a separate study called weld sizing. Everything here is the same. You'll only see this addition right here. So there's a new connectors folder where I've added the edge weld connectors. So you can actually see I have 3 edge weld connectors in here, located right in this region where we just showed the high stresses. And if I right click and kind of show the setup here, so it's a single-sided fillet weld, and you can see the faces that were selected here, and then that edge showing right there, and then it's oriented on the upper side here. I've selected an electrode, a steel electrode, and I've input a safety factor of 2 and an estimated weld size of 1/4 inch. And that's the same for all 3 segments here. You can see if I hover over one of these, it actually lists all that information, so I can see it in the viewing area as well. So that's the only change I made. I've replaced those bonded contacts with edge weld connectors in that region, so I can get that weld check plot. So I've already run this as well. So we'll take a look at the stress on this one. Again, we see the high stress area over here, but now I can also view my weld check plot that I've created. So you can see up here, I have two welds that need attention and one that's okay. So you can actually, if I click on that one, it shows me right here, this first segment here is passing right now. It's calculated weld size of 0.23 inches, so just under my estimated of 0.25. The others that need attention are just over that, so 0.254 and 0.2588. And again, I can check those using my plot right here. So you can see this one, the max is about 0.23. And for my failing welds, so if I go up here and select, go down to my second connector here, you can see that the first about 2 inches of the weld along the weld seam is where I have that above 1/4 inch calculated weld size. Okay, so those were 2 examples kind of showing a simple example and then a little bit more realistic example of how we can use the edge weld connectors to estimate or determine our required weld sizes and check our weld strength based on the forces in those locations. One more thing I wanted to show here was some different alternative methods for modeling welds. So an edge weld connector basically creates a bonded contact along that edge. So here I'm showing I've got basically a beam here with a base plate, and I've defined this using an edge weld connector. So if I look at my stresses here, and I'll actually turn off the symbols, we can see it there. You can look at the von Mises stress over here. Again, you'll see these singularities along the edge. That's going to happen anytime we have a bonded contact along an edge. If I compare this was the edge weld connector. If I compare this with just creating a bonded contact on that edge, I get basically the same results. So I'm just showing there a bonded contact is basically doing the same thing as the edge weld connector. The difference with and the real functionality of the edge weld connector is we get that edge weld, or sorry, that weld check plot, so we can check those forces in that area. The only other alternative we would have would be to actually fully model the edge weld, and I'll show that here. And I've kind of isolated the weld, but again, we'll still get those singularities on that edge in those high stress regions. Basically, if you think of it like the stress is basically a force over an area, and if the area in those regions is going to 0. So in any type of FEA, we'll always have singularities along those edges. So something to note when you're doing, any type of simulation involving welds, if you see those local high stress regions, just realize that that's most likely a singularity due to that, due to the sharp edge there. So that's all I had. If there are any questions, I can address those at this time.
Hey, Tim.
Yes.
Hello, Tim. Can you hear me? Yeah, this is
you.
Dean Schultz with Alignex. Okay, I've got the questions out in front of me here. Some people have asked. We might not have time to answer all of them, but we can certainly run down the list here, and there's a handful of different ones.
Sure.
And then at the end, I guess, we started about 7 minutes late, so we are running a little bit over, and that's fine, though. So here's a couple questions. It says does the edge weld connector work where a gap is modeled in?
You can use an edge weld connector in a gap as long as the gap is not too large. And the reason is that the equations that the edge weld connector calculations are based on is for basically in contact. So the edge weld connector that is meant for in contact welds. You can use it where there's a gap as long as the gap is not too big. And actually won't
like 0.03, would that be acceptable?
0.03.
As far as the gap? As far as the
3
gap.
inches?
Yeah.
I guess it would depend on the situation. The orientation of the parts sometimes plays a role in whether it will let you select those edges for an edge weld. If you can't select it for an edge weld connector, you can still create a bonded contact in that region. You just won't get the edge weld check plot.
And then a couple of things about the safety factors. Are the factors of safety, are they defaulted to 3 and 5, and can they be changed?
So if I jump back a slide here, the defaults for these are the 2 default options, and they have default values of 3 and 5. But again, you can enter any value you want. If I jump back here,
right,
I can go in and I can override that down here.
And converting a solid to a shell?
Yep.
How's that done?
Okay, so right here, if I right-click, I can define shell by selected faces, and what I'd actually do is I'd go in and pick a face. That'll be the shell face, and then I can go in and specify a thickness right here. And if the parts were created in sheet metal, they'll actually come into SOLIDWORKS Simulation as shell automatically.
Great. Well, how do you select the faces and edges for the edge welds in the second example?
In this example?
Yeah, I believe that was the second. Yep.
Sure. Okay. So we'll take a look here. So in this case, face 1 was actually this bottom face right here. This is the terminating face. Face 2 was this whole, everything that's blue right here, this side piece right here, and then it automatically detected that edge between those faces.
And we've got time for a couple more, and then, but one says here, I like how SOLIDWORKS shows us the 3 orthogonal forces, max and min of each, but can we see a vector addition sum of those forces and where along the weld those forces and sums reach their max and min values?
So to get the resultant force, it's not going to plot that automatically, but you can basically figure out what the resultant force would be because you have all the, like you mentioned, the orthogonal forces here. So you could, you have the components of the resultant vector. As far as the forces along the weld, that's kind of what it's showing in the check plot. So the areas where it's showing the highest calculated weld size required, that's going to be the area with the highest forces acting on it. So obviously, you're probably not going to vary your weld size along the seam. You're probably going to pick the max here. So in this case, you might pick 0.24, a quarter inch, something like that. But this is kind of showing you how the forces, roughly showing you how the forces are varying because it's calculating the required weld size along that seam.
Now, I'm going to wrap up with this last question here, and then the ones that didn't get answered, we can go back to everybody because we have the person who asked the question. But there's one people are asking about stitch welds instead of going all the way around, and like they use a lot of welds, they say where they go like 1 inch weld every 3 inches or every 9 inches or something like that. Is there a good way to do that?
Stitch weld, there's no way to directly model stitch welds you can't use an edge weld connector. You could possibly do it with a bonded contact. You'd have to set up some local bonded contact sets there. or you could also potentially actually model the stitch weld with a, kind of like I showed here with using a fillet. So if you did a fillet and then patterned that along that edge, there may be a way you could do it, but no, there's no way to directly do a stitch weld. There are spot welds in SOLIDWORKS to do two flat surfaces, but that's the only other type of weld connector.
Okay. Well, excellent. Why don't we put up the product slide here, and then I'm going to wrap it up for you. Excuse me. You know, thanks for attending today, everyone, and we've got questions to get back to you on, and we'll certainly do that. Just so you know, there's a couple of things we would like to do. We've been doing these webinars over time, and we'd like to use your topics. So one thing, if you'd like some different topics that you'd like us to do, you could send those to us at info@. And same thing with inquiries as far as if you'd like to learn more about simulation. There's the info@alignex.com. But also if you'd like to learn more about the other products, feel free to either you can work with your sales rep, or you can just go to info@alignex.com, and we can talk about what comes with, besides the weld sizing capabilities, but all the other kinds of simulation that you might be interested in. And then there is some special pricing as far as if you're buying a seat of SOLIDWORKS right now, just know that you could buy the Simulation Professional for $1,000 and add that in, and you know, big savings of money right now. You can upgrade existing license that you have also. So any of those kind of questions, feel free to get a hold of us, and we'll get back to you. Again, though, thank you for attending, and at the same time, please send any feedback you have to us, and we'll take that in consideration and try to put the next shows on with your topics. Thank you, everyone.